Hi all, today we are going to study about working principle of DC motors and their power and torque relations. All of you know from your school classes itself that an electric motor is a machine which converts electrical energy into mechanical energy. The basic working principle of an electric motor is when a current carrying conductor is placed in a magnetic field, it experiences a force. The magnitude of force is given by the relation F is equal to BIL sin theta, where theta is actually the angle between the conductor and the direction of magnetic flux. B is magnetic flux density and I is the current, which is actually flowing through the conductor. L indicates the length of the conductor. The direction of mechanical force is given by Fleming's left hand rule. In Fleming's left hand rule, the middle finger indicates the direction of current, the forefinger indicates the direction of magnetic flux, and the thumb indicates the direction of mechanical force. Even though all of you know that whenever a current carrying conductor is placed in a magnetic field, it experiences a force. But you are not aware how is it happening. Let's see that in these two diagrams. Here a current carrying conductor is placed in a magnetic field. This is actually a bipolar machine. And the direction of current is into the conductor. So by using right hand thumb rule, you very well can identify the direction of magnetic flux is clockwise. Hence the magnetic flux produced by the conductor is also indicated here. So now in this system there are two fluxes. One is the flux which is produced by these magnets and the other is actually the flux which is produced by the current flowing through this conductor. If you see at the left side of this conductor, both these fluxes are in same direction, whereas at the right side these two fluxes are in opposite direction. So definitely there occurs a crowding of magnetic flux lines at the left side, and at the right side there occurs a narrowing of magnetic flux lines. Due to the strengthening of flux at the left side and weakening of flux at the right side, this flux distribution acts like a stretched rubber band under tension. This exerts a mechanical force on the conductor from high flux density area towards the low flux density area. This is how a current carrying conductor when placed in a magnetic field is experiencing a force. Here for understanding purposes we have considered a permanent magnet and a single current carrying conductor, but in actual practice it's not like this. In actual practice we will be using electromagnet and numerous conductors will be placed over the armature. Each conductor placed on the armature will experience a mechanical force. Due to this, overall armature experiences a twisting force called torque and the armature of the motor starts rotating. In order to understand thoroughly the basic working principle and the direction of mechanical force, I have explained here the reversing the direction of rotation in a motor. Here if you see in case 1, the direction of flux is upwards and the direction of current is into the conductor. Now applying Fleming's left hand rule, you will be able to identify the direction of mechanical force experienced by this conductor is towards right side. If you want to reverse the direction of mechanical force, then either the polarity of this magnetic poles has to be reversed or the direction of current in the conductor has to be reversed. You see case 2, comparing with case 1, in case 2 the direction of current in the conductor has been reversed. Now the direction of current is out of the conductor, and again if you are applying Fleming's left hand rule here, you will be able to find the direction of mechanical force experienced by this conductor is towards the left side. Now consider case 3. In case 3, the direction of current in the conductor is same as that of in the case 1, only the difference is the polarity of the magnetic poles has been reversed. Now you will be able to see the direction of force experienced by the conductor is towards left side. So while comparing with case 1, case 2 and case 3, if you want to change the direction of mechanical force experienced by the conductor, either the direction of current flowing through the conductor has to be reversed just like as that of in case 2, or else the direction of polarity has to be reversed as in case 3. If you try to reverse both the polarity and the direction of current in the conductor simultaneously as in case 4, On applying Fleming's left hand rule, you will be able to find the direction of force experienced by the conductor is towards the right side. So it's very clear while comparing case 1 and case 4. If you try to reverse both, then definitely the direction of force will remain in the same way or in the same direction. If you want to reverse the direction of rotation, either you have to change only the polarity of the magnetic poles, or you have to change only the direction of current flowing through the conductor. Either one of them should be changed. Next we are going to study about back EMF. This is a very important topic. During motoring action, when armature rotates, armature conductors also rotates, and hence it cuts the magnetic flux and an EMF gets induced in the armature conductors. There is occurring a generating action in a motor according to Faraday's law of electromagnetic induction. The direction of induced EMF is always opposite to that of the supply voltage, which can be found out by using Fleming's right hand rule. As the direction of induced EMF is opposite to that of the supply voltage, they can be represented by a battery connected across the supply mains as shown in this figure. Definitely the magnitude of V is greater than back EMF, hence the direction of current will be like this. The magnitude of this induced EMF or the back EMF can be determined by using the same relation of induced EMF which we have generated or which we have derived in the DC generator. That is Eg is equal to 5 Pn Z by 60A. The same relation can be used to find the magnitude of Eb also, that is back EMF. So from this electric circuit, by using Kirchhoff's voltage law, you will be able to find the relation for Ia, that is Ia is equal to V minus Eb by Ra. Or else I can write the voltage equation as V is equal to Eb plus Ia Ra. If I am taking the brush drop also into consideration, then definitely the relation becomes Eb plus Ia Ra plus brush drop. This is the current relation just like I have mentioned now, which is obtained from this voltage relation using KVL, that is Kirchhoff's voltage law. If you see this relation, the magnitude of Ra is very small. So definitely under running condition, the difference between Va and Eb also must be a small value. Otherwise the magnitude of current becomes infinitely large amount, which causes the damages of the machines. So in order to avoid that, under running condition it must be ensured that the difference between V and Eb must be also very small. Next we are going to see the power equation of a DC motor. The power equation is derived from the voltage relation. In this voltage relation you have to multiply both left hand side and right hand side with armature current. Then you will be getting the relation like this. VIA is actually the input power which is being provided to the DC motor. Ia square Ra is the copper loss which is occurring in the armature resistance. This Eb into Ia is actually the electrical equivalent of mechanical power developed. That is, this is the electrical part which is getting converted into mechanical energy. Next we are going to obtain the condition for maximum power. To get that, you have to derive the standard relation. From the power relation, I have told you that Eb into Ia represents the electrical equivalent of mechanical power. So I can write, instead of Eb into Ia, I can write it as Pm, that is the gross mechanical power developed, that is equal to V into Ia minus Ia square Ra. Now I have to obtain the condition for this maximum power, that is the maximum mechanical power. To get that, I have to do the first derivative of it and equate it to 0. So I am finding out the first derivative of this mechanical power developed. So I will be getting the relation like this. See, I am doing the derivation of this with respect to Ia. So the right hand side becomes V minus 2Ia Ra, and I am equating it to 0 because I am finding the condition for maximum mechanical power. You have already studied about this in your engineering mathematics also, the condition for maxima and minima. To get that, you have to do the first derivative and equate to 0. So from this I will be getting the condition for maximum mechanical power developed as Ia Ra is equal to V by 2. From the previous slide we have studied the relation for back EMF, that is Eb is equal to V minus Ia Ra. So in the condition for maximum power, IARA is same as that of V by 2. So from here I will be able to get the relation for back EMF as EB is equal to V by 2. Because in the relation, in the standard relation V minus IARA, I am substituting for IARA as V by 2. So it becomes V minus V by 2 and I will be getting the relation for EB as V by 2. So this can be said to be the condition for maximum mechanical power developed. But this condition is not realized in practice. From the standard relation of current which we have obtained in the previous slide, that is IA is equal to V minus EB by RA. In this maximum power condition, the value of EB is same as that of V by 2. So in that particular instant, if you try to find the magnitude of current, that is IA is equal to V minus V by 2 by RA. So the numerator portion V minus V by 2 becomes V by 2. So IA is equal to V by 2 by RA. In that the V by 2's magnitude is very large comparing with that of the magnitude of RA. Then due to which a very large magnitude of current will be flowing through the armature, which results in the burning of the armature conductors. So in order to avoid such problems, we never try to run the machine in the condition for maximum power for a longer duration. Next we are going to obtain the torque equation of a DC motor. The gross torque developed in the armature is represented by TA, that is T suffix A. As we know from the previous slide, the electrical equivalent of mechanical power developed is EB into IA. So to find the relation for torque, I will be equating the electrical equivalent of mechanical power, that is EB into IA, with the standard relation of mechanical power, that is torque into omega, that is EB into IA is equal to, since this torque is developed in the armature, we are indicating it as T suffix A. Omega can be represented by 2 pi n by 60, where n is speed in RPM. The relation for EB, that is back EMF or induced EMF during the motoring action, is same as that of the generated EMF which we have studied in the case of a generator. So instead of EB I can substitute as 5 pi n Z by 60A. So after making the substitution, the relation becomes like this. From this relation the 60s gets cancelled, this n terms also gets cancelled, and finally you will be able to obtain the relation for TA as 1 by 2 pi phi IA into PZ by A. The magnitude of 1 by 2 pi is 0.159. You can check that in the calculator also. So finally the relation for torque developed is 0.159 phi ZIA into P by A. This is a very important relation. You have to by heart it, then only you will be able to solve the problems associated with it. Next we are going to obtain the relation for shaft torque. This is actually the torque which is available for doing the useful work. This is not same as that of the armature torque developed. The final mechanical output power which is available at the shaft is given by this relation, that is shaft torque into omega. From this shaft torque can be written as output, that is the output power which is available at the shaft divided by 2 pi n. If the speed is in RPS, if the speed is given in RPM, there is a mistake here. Here it is n is in RPM. If the speed is given in RPM, then definitely the relation becomes 2 pi n by 60. Then bringing this term to the numerator, you have to multiply it with its reciprocal. So the relation becomes like this. 60 by 2 pi, if you calculate, you will be able to get it as 9.55. So you can write the shaft torque relation as 9.55 into output by n. You must remember this relation also. Definitely the magnitude of shaft torque will be definitely less than the armature torque developed. If you are subtracting iron and friction losses of the motor from the armature torque developed, definitely you will be able to get the shaft torque power. Next we are going to analyze this speed and this armature torque relation. If you see from the back EMF relation, that is back EMF is equal to 5 pi n Z by 60A. So from there I can easily write speed n as directly proportional to EB by phi, or I can write it as speed is equal to K into EB by phi, as I have written here. From the standard relation of armature torque which we have derived before, that is TA is equal to 0.159 phi z Ia into P by A, it's very clear that the armature torque developed is directly proportional to phi Ia. So if you see here, speed is inversely proportional to phi and the armature torque is directly proportional to phi. So if you try to increase the value of this flex, you will be able to see very clearly that the armature torque developed will be also increasing. But when you try to increase the magnitude of this flex, from this relation it's clear that the value of speed will reduce. So this seems to be a controversy, because when actual torque is increasing, motor speed must also increase rather than decreasing. But if you see here, if I am trying to increase the value of flex, then the torque is increasing, but if I try to increase the value of flex, the speed is decreasing. This seems to be contradictory, and the explanation for that is given here. But the explanation given here is with respect to the reduction of flex rather than increase in flex. Let's see. If you are trying to reduce the value of magnetic flex, that is phi, then definitely the magnitude of EB, that is back EMF, also drops, because back EMF is given by phi Pn Z by 60A. So definitely if you try to reduce the value of phi, then the magnitude of EB also drops. Due to the decrease in EB, from the standard relation of armature current, you know it very well, Ia is equal to V minus EB by Ra. So due to this decrease in EB, definitely the magnitude of Ia also increases very large. So in this relation, we have tried to reduce the value of this magnetic flex, but when you try to reduce the value of this magnetic flex, it results in a large change. That large change is actually large increase in the magnitude of armature current. So the small change in the flex value has been counterbalanced by this large increase in the armature current, which results in the net increase of torque. And if you see here, if you are trying to reduce the magnitude of flex, then definitely the magnitude of speed is increased. So even though you have tried to reduce the magnitude of the flex in this relation, there occurs a large increase in the magnitude of Ia, which causes the overall magnitude of torque to increase, and this further causes the speed to increase. So the contradiction has been removed now. Before it was told that if you are trying to reduce the value of this flex, then the magnitude of torque reduces, and if you try to reduce the value of flex, the magnitude of speed will increase, which is actually not supposed to happen. Whenever there is occurring a decrease in the torque, the motor speed must also reduce. So from this explanation, it's very clear, when I am trying to reduce the value of this flex, the value of this armature torque is increasing. From this relation also you will be able to see the motor speed also has been increased. Hope it's clear for you. This is actually a very important concept which you must understand. Next we are going to see some numerical problems associated with the relations which we have studied in today's class. Let's see the first question. A 220 volt DC machine has armature resistance, Ra's value is given, and the full load armature current is 20 ampere. Ia's magnitude is given 20 ampere, and it's asked to find the induced EMF if the machine is acting as a generator as well as motor. Whenever such problems are asked, it's better to make a diagram of both of it, that is the DC generator as well as DC motor. Here the generator voltage is 220 volt, and in the case of motor the supply voltage is 220 volt. Actually the direction of current which is given here is wrong. This current direction must be downwards like this. In the case of only in the case of generator, we will be able to supply the current from the brushes. In the case of motor, we are actually feeding the current to the brushes. So from the standard voltage relation of a generator, you know it very well. That is V is equal to Eg minus IaRa. From there you can easily find out the relation for Eg. Eg is equal to V plus IaRa. You have to make the substitution for V, Ia and Ra here. The magnitude of V, Ia and Ra are given in the question itself. So if you are making the substitution, you will be able to get the value of generated EMF. So that is the induced EMF when the machine acts as generator. Next you have to find the magnitude of induced EMF when the machine is acting as a motor. That is, you have to find the value of back EMF. The value of back EMF can be found out from the standard relation Eb is equal to V minus IaRa. So you have to use that relation here. And you have to make the substitutions, then you will be getting the final answer. That was a simple problem. In this problem, the machine rating is 25 kilowatt, 250 volt. DC shunt generator has armature and field resistances of 0.06 ohm and 100 ohm respectively. There is the magnitude of Ra and RSH, both are given. And it's actually a shunt generator. So you have to draw the diagrams first. Then it's asked to determine the total armature power developed. You have to find the total armature power developed when working as a generator and motor, both at 25 kilowatt. So let's see the first case of a generator. So the generator is delivering 25 kilowatt and the terminal voltage is 250 volt is also given. So from here you will be able to find the magnitude of load current, because 25 kilowatt divided by 250 gives the load current value, that is 100 ampere. This 250 volt will be the same voltage which will be appearing across this terminals as well as this terminals, as these three are in parallel. The magnitude of this shunt field resistance is also given, that is 100 ohm. So if you are applying 250 volt across this shunt field winding resistance, then the current which will be flowing through will be 250 divided by 100, that is 2.5 ampere. So the field current is 2.5 ampere and the load current is 100 ampere. From here you will be able to calculate the armature current, because armature current will be the sum of these two. This you have already studied in the case of different types of DC generators video session. So Ia, the armature current magnitude in the case of this DC generator is 102.5 ampere. You are asked to find the total armature power developed. In the case of this generator, the total armature power developed will be the product of the generated EMF and the armature current, that is Eg into Ia. The magnitude of Eg is not given in the question, you have to calculate it here. That you will be able to calculate from the voltage relation, that is Eg is equal to V plus IaRa. The value of V is very clearly given here. Ia's value you have found out, 102.5. Magnitude of Ra is given in the question, 0.06 ohm. So you will be able to find the value of Eg, that is 256.15 volt. So now you can find the power developed in armature as Eg into Ia. This is also actually a mistake, it is not Eb, it is Eg. So Eg into Ia, by making the multiplication of this 256.15 into 102.5, you will be able to get the power developed in armature when the machine is working as a generator. Here a 1000 division has been done to make it or to convert it into kilowatt range. Next you have to see, or you have to calculate the value of armature power developed when the machine is working as a motor. So in this case the relation will be Eb into Ia. So you have to find the value of Eb. The magnitude of Eb can be found out by using the relation Eb is equal to V minus IaRa. So before that you have to calculate the value of Ia, because in this case it's clearly given that the motor is taking 25 kilowatt input power. The terminal voltage is 250 volt since it is taking 25 kilowatt input power, definitely the current taken by the motor will be 100 ampere. And the current which is flowing through the shunt field winding is 2.5 ampere, which remains fixed both in the case of DC generator as well as DC motor. Or you can easily calculate it in both these cases by simply dividing this voltage with the shunt field winding resistance. So if you subtract this 2.5 ampere from this 100 ampere, you will be able to get the current which is flowing through this armature, that is 97.5 ampere. Please don't make the mistake. In the case of generator, the armature will be supplying the current, and by using Kirchhoff's current law or Kirchhoff's nodal rule, you will be able to find the current which is coming here will be splitting into two portions, and one will be flowing through the field winding and the other will be going towards the load side. In the case of DC motor, the motor terminals will be taking the current from the supply, and the current when it is reaching this node will get split into two. One is flowing towards the field winding and the other is going to the armature. So please understand the splitting or the direction of current flow in the case of generator as well as motor. Don't get confused with this. So in this case, now we have calculated the value of armature current. Next we have to find the value of back EMF. In the case of DC motor, the back EMF can be found out by using the relation EB is equal to V minus IA RA. All the parameters in this relation is known now. So now you can simply substitute and you can find the value of EB. Then by multiplying that EB with IA, you will be getting the power developed in armature. Let's see the next problem. A DC motor takes an armature current of 110 ampere at 480 volt. Armature circuit resistance is 0.2 ohm. RA's value is given. IA's value is also given. Terminal voltage is given as 480 volt. That is V. The machine has 6 poles and the armature is lap connected with 864 conductors. The flux per pole is 0.05 Weber. The magnitude of phi is also given. It's asked to find the speed first. Second, it's asked to find the gross torque developed by the armature. That is the magnitude of TA. So let's calculate the speed first. The speed can be calculated from the relation of back EMF, that is 5 P and Z by 60A. The value of Z is given here, that is the total number of conductors, and the magnitude of A, it's very clearly given that it's lap connected. So in the case of lap connected, the number of parallel paths is same as that of the number of poles. So the value of A is 6. Now making the substitution, phi is given, Z is given, the value of P and A is given. You have to calculate the value of N. But before that, you have to find the value of EB. In the case of a DC motor, the back EMF can be found out from the standard relation of voltage, that is EB is equal to V minus IA RA. IA's magnitude is given and RA's value is also given. V is also given. So from here you will be getting the magnitude of EB, and after getting the magnitude of EB here, you will be making the substitution in this relation, and then from here you will be getting the value of speed as 636 RPM. Next we have to calculate the relation for, the magnitude of gross torque. The relation for gross torque, we have already derived it as 0.159 phi ZIA into P by A. You have to make the substitution here, and then you will be able to get the value of TA. This is also a simple problem. Only thing is you must know these relations. Then only you will be able to solve these problems. In the next problem, you are asked to find the developed torque and shaft torque of 220 volt 4 pole series motor. It's very clearly given that the machine is series motor with 800 conductors. Z value is given. Wave connected, so it's clear that the magnitude of A, the number of parallel paths, is 2. A load of 8.2 kilowatt by taking 45 ampere from the mains. Flux per pole is given and the magnitude of RA is also given. So developed torque can be found out by using the standard relation 0.159 phi ZIA P by A. After making the substitutions, you will be getting the value of TA here. Next, you are asked to find the shaft torque. You very well know that the shaft torque into omega gives you the output mechanical power. So you have to find the value of N, then only you will be able to calculate the value of TSH, that is the shaft torque. The value of N can be found out from the standard relation of back EMF. So in the next step, you have to calculate the value of back EMF. Back EMF can be found out from the standard relation V minus IARA. In the case of a series motor, the supply current or the current which is being taken from the supply is same as that of the armature current as well as the current which is flowing through the series field winding. So I will be able to write the relation for back EMF as 220 minus IA is given in the question itself, 45 ampere into 0.6. So you will be able to get the magnitude of EB as 193 volt. Then you can find the value of N by using the standard relation 5PNZ by 60A. Making necessary substitutions, you will be able to calculate the value of N as 4.825 RPS. Since the speed you have obtained here is in RPS, you have to use 2 pi N in this relation for omega rather than 2 pi N by 60. 2 pi N by 60 will be used when the speed is given in RPM. And the output power is also given supplying a load of 8.2 kilowatts. So you can make the substitution for TSH. You can make the substitution for N here and for output power here, that is 2 pi into 4.825 into TSH is equal to 8200. From here clearly you will be able to find the value of shaft torque, which is 270.5 Newton meter. With this, we are completing today's session. All of you must be familiar with the derivations which we have told in this class. And you must by heart the relations for torque, power and voltage. Then only you will be able to solve the problems associated with it. Okay, thank you.